Hello, it's Brian from Tavaran Games here with episode 7 of our strategy map generator tutorial. So in this tutorial, I want to cover the basic pathfinding script. So basically getting a unit from point A to point B around water and mountains and things that it can't get through. We won't get to the more advanced features of having this line drawing to show potential paths, or the fact that the pathfinding script actually compensates for having moved the map over and can still pathfind regardless. But we will cover the point A to point B pathfinding, and we're going to be using an A-star pathfinding algorithm. Now, to figure out how to do that originally, I followed this Code Monkey video on A-star pathfinding, his tutorial, and he does a great job of explaining how the pathfinding works and how to put it into your own game. Now, I adapted that to work on the hex-based grid of the strategy map we're generating, as well as to work with the offset of the map, though we won't get into that in this episode. Okay, so let's get started. Let's go back to our tutorial version, and we're going to need a few new scripts. So 3 of them for the pathfinding. One is the path node itself. That's the data for each hexagon and the information we need for its pathfinding data. We're then going to have a path grid script, and that's going to contain the overall grid of tiles and all the path node information that's within it. And then we're going to need the actual pathfinding script, and which is going to do all of the work using the path node and path grid data. So the first thing we want to do is let's open up this path node script. It's empty. It's not a mono behavior. We want to get rid of that. We want to get rid of the start and update. We don't need that at all. This is going to be a new class, and it's going to contain our path node data. So the first thing we're going to need is our position. We'll do that as a vector 2 of the position. And that's going to be the exact tile position that this path node corresponds to. We're then going to need our path node variables. So I'm going to use the same names that Code Monkey did. So we have the G cost, which is going to be the cost it takes for the unit to get from the starting node to this node following a applicable path, a viable path. We are then going to need the H cost variable, also as a float. And that is going to be the distance from this tile as the crow flies to the end tile. And then we're going to need the F cost, which is just going to be the addition of the G cost and H cost together. And we're going to use that to track what is the best tile for us to look at in our pathfinding script. And as we write the pathfinding script, you'll understand more what these numbers are doing. We will also need a path node itself as the node that this one came from. So this is going to be, as we pathfind, we're going to record, if we get a viable tile, we're going to record how we got to that tile, the previous node of how we got to that tile. The other thing we're going to want is we want to know, is this a passable tile? We're actually going to do this as an integer because in the strategy game, we're going to have different land types. We have the water, we have mountains, we have flatlands, we have forests, we have hills. And so we have multiple different basically levels of pathfinding, and different units can possibly cross them. So a plane can probably cross anything, but a unit on foot that has no boats and no technology for that is only going to be able to cross sort of flat land and forests and that, and not cross the mountains and water tiles. And then as you add to the game, you add naval units in that, you're going to want to be able to track what each unit individually can pathfind through. So we can use an integer to track, okay, what is this tile, what's on it, and then we can use the unit data to tell it, can the unit go through this tile? Okay, so we need our constructor. So that's going to be a public path node, and it's just going to take in a vector 2 of our pause data. And then all we need to do is do this dot position. So that's going to be this position up here is going to be equal to this position we just fed into it. There we go. The other function we're going to need eventually, so we might as well write it now, is just a quick function to calculate our F cost for the tile. So that's really simple. Just F cost is equal to G cost plus H cost. All right, so that's all the code we're going to need in our path node itself. So this is just a new class. It's going to be taking in the data that our other scripts are going to use. Okay, so let's open up next our path grid, and let's actually draw out a grid of those nodes for us to access with the pathfinding script eventually. So this one is going to be a little bit bigger. So we are going to declare our grid as a private variable because we don't want any other scripts messing with it. And it's going to be an array, so a two-part array. So it's going to take an x and a y value, basically the coordinates. And we're going to be able to search through that array and find our path nodes based on the x and y values we put in. So we're also going to need the size of our map. So we're going to need a public integer for the width of the map, and we're going to set that equal to 0. We're then going to do the height of the map as an integer as well, and that's also going to be 0. We're just going to set that to 0 and 0 because we're going to use the map maker to tell the grids what size it's supposed to be, and that's why these are public. Now, the other thing we need is we need to get our default layer as a layer mask, so that way when we're checking each tile, we don't have to redeclare that. We're going to be doing this for a lot of tiles, and this will just be a little more efficient, I think. And then in the start, we are going to grab our default mask. It's going to be equal to a layer mask dot get mask default. Okay, so we got that set. We're not going to use the update function yet. We will use it soon to actually do a debug drawing of our grid, but let's write that after we actually do the code to make the grid. So we're going to make this a public void because we want to be able to call it from our map making function when after we've made the map, so we can then correctly define the grid by whatever our new map is. So we're going to declare grid is equal to a new array of path nodes, and that's going to be equal to the width and the height of the map that we feed in again from the map maker. And now we're going to do our dual for loop through that for int x equal to 0, x less than width, and x plus plus. Let's do that for our y inside of that. Less than the height, and then y plus plus. So we've done this a million times in a bunch of different scripts. So we're doing it again. Okay, so we need to, of course, do our positional correction. If you're in a square grid, you don't need to do this because all of your tiles should be on your just integer xy coordinates. But because we're the hex grid and every time we've had to do it, we've had to move over tiles into float values, so 0.5 and half the x rows and times 0.86 for the y. We need to do our positional correction yet again because we're going to store that data in the path node. So first, let's just make a vector 2 of the xy. Let's do our x compensation. So y remainder 2 is equal to 0. We are then going to add to the x, posit x plus equals 0.5f. And then we're going to multiply the pos.y times 0.86f, as we've done before. Okay, so we need to establish our new grid. So at the x comma y, so you have to use the integer coordinates for the keys for the grid. And then we're going to make that equal to the new path node, and that's going to be the pos we just calculated. So we feed that in, and the position of the path node is going to be equal to the actual camera coordinate position, whereas the x, y values in the grid are going to be equal to the values of a square grid. So we're going to need to compensate in another couple functions for that. But we are going to have the actual position that we can use for unit pathfinding stored here. So the next thing we're going to do is we're going to declare a new integer for the open value of that tile. We're going to set that to 0. So 0 is going to be any tile that is passable by any land unit. So we're going to use that for the flat lands. Now we need to check, is the tile we're looking at something that is not completely open? So we're going to do a raycast, as always. Raycast hit 2d. Hit equals physics 2d.raycast, and then we're going to use our position we calculated, put that in for the direction as well because it doesn't matter, and then we have our default mask. Okay, so if we hit something, again, the default is only the tiles, so if we hit it, we know it's a tile. And so we're going to check the type of the tile, so GameObject.get component. And we're going to grab the hex type where that data is stored and type. So if it is equal to 4, if it's a mountain. So the mountains, we want them to be very difficult to pass. The only thing that should be able to get over those are like airplanes. An ocean, which is type equal to 0, we then let's make that 7 for now, because we can write in our naval units later, but we're going to keep the ground units for like 0, 1, 2, 3. Naval units can be slightly higher numbers, and then really hard to pass the highest. The other thing we're going to do is for forests and hills. We're not going to actually make this do anything yet, but we want to actually record the data. So we're going to say if there's a forest present, we're going to do open plus equals 1. And we're going to do the same thing if there's a hill present. And again, this isn't an else if statement. We're going to be checking for both. So this way, if there's a forest, the difficulty is 1. If there's just a hill, the difficulty is 1. But if there's a forest and a hill, the difficulty is going to be 2. So we need to place that value into our grid position dot open is equal to open. And now we're finally going to use our old open value we declared up here as well. Because if we ever need to change the open value of a tile, like say a unit steps onto it, when the unit leaves that tile, we want to make sure we go back to the correct value and don't have to recalculate it. So we're just going to store the value we want, old open, so say it's a forest, it's going to be 1. A unit walks onto it, we can make it a 10, and then the unit walks off. This value will be able to turn it back into a 1, or a 2, or a 0 for whatever it is. Okay, so we have our grid is now set. This is the data we mainly want for our pathfinding, is how open the tile is. But we have no way to actually visualize it at the moment. So we're going to use a debug style draw line function to draw a line on each tile with a different color based on how easy it is to pass. But we don't want to do this all the time, so we're going to use a boolean to tell it, do we even want to do this, which we can just turn off, so that way we don't have to delete the code and recode it if we ever want to debug using this. And we don't want to draw it every single frame, so we're going to give it a delay so it only draws once in a while, maybe twice a frame instead of every single frame. So each frame we're going to subtract the time, the frame time from delay. Yep, delta time. And then if we want to draw the grid and our delay is less than 0, we then want to actually go through the grid and draw on the, basically the data, the open data. So let's put this here. We're going to copy our loops from before, re-bracket those. Okay, so the way we're going to draw the line is we're going to first check what line we need to draw. So we're going to look at the grid X, Y, and we're going to see if the open is equal to 10. We'll do the mountains first. And then we want to do debug.drawLine is the function we want. And we're going to go from our start position to end position. So the start position is going to be our grid position. So grid x comma y dot pause. We're going to subtract from it a vector 2 of 0.5f to 0.5f. So that way it's going to be sort of on one bottom corner, sort of on the tile. Oh, this has to be a new vector 2. And then we're going to copy that. We're going to do the y, or the other corner, as a plus. And now let's make this a red line for the mountains. And we're going to tell it to go away after half a second. Okay, so we can just copy this, and we're going to do an else if. So we'll copy it, do the else if open is equal to 7 for the water. Let's do that next. Let's make the water yellow, so it's visible on top of the water. And then we will do the open land, so that's 0. We're going to make that green for go. And then finally, we're going to do anything else. So let's just make this an else statement. And that's going to be cyan. That's going to be our hills and forests and stuff. So let's save that. So we have that. Now we need to actually call the path grid. So we're going to do it over in the map maker script. We're going to do a new function of draw grid, the same as we called it before. And now we're going to attach the path grid to the camera. So we just need to get component, our path grid. Now we're going to need to set the width and height first. So we're going to do the width is equal to integer of the map size dot x. We're going to set the height as well. Copy that. And then make this a height and an integer of the map size dot y. And then we are going to run the draw grid function in there. And now we want to run this script after we've done our add mountains, because that's the last part of our map making. And we definitely want the mountains in place and finishing their growth cycles before we actually draw the grid. Otherwise, it's not going to take them into account, and it's going to think all the land is walkable. So we're going to do an invoke, as we've done before, at time.delta_time. So make sure that's all happy. Save that. Everything's saved. Let's go back into here. And on our main camera, we're going to attach our path grid component, so we actually have it. And the map maker should tell it to run, so let's give that a go. So the map generated, that looks fine. Let's go to scene view, and look at that. We have a grid. So all the ocean tiles have yellow lines. We have green and cyan lines here. The cyan looks a lot like the green, but it is a little bit different. And then our mountain tiles, there aren't many, but they are marked in red. Okay, so our grid generated correctly. So now we need to be able to pathfind on that grid. So let's save this. Let's open up a pathfinding script, which is empty. And this is going to be a mono behavior as well, like the path grid. And let's start writing that. So the first thing it's going to need is, well, the grid. So we're going to just set this as a public thing so it can be accessed. And we can set it from elsewhere if need be. So the grid. And we're going to need two lists. We're going to need a list of path nodes for open nodes. So these are going to be nodes we have yet to fully evaluate, but we have calculated the costs for, and we're going to make this a new list path node. And we're going to need our closed nodes, and that's where we're going to store all the nodes we have fully looked at. We have checked if they are our endpoints, and once we find the endpoint, we can then go through our closed nodes and grab the path that we've calculated. So in the case of the start, we're going to set our grid we can get it from our get component, because we're also going to attach this to the camera itself. We're not going to attach this to a unit. We're just going to have one pathfinding script attached to the camera that the units can call when they need it. Okay, so we get the component path grid. We've got it. All right, we don't need update. That can go away. What we do need is a new function to actually get our path. So in this case, we're going to be writing in a few different places. What we're going to want to return, though, is a vector2 list of our actual coordinates we want the unit to walk to. If we return a path node list, then we have to have the unit get this grid and grab the coordinates from the path node. I would rather do that in this script and just return the vector2 coordinates themselves that the unit can use. So what we're going to put in, though, is we are going to use a start position as a vector2, so it can just be wherever our unit is located. We can then go to an end position, so that's going to be whatever tile we click on that we want it to move to. And then we're going to take an integer. We're going to just call this unit type, but what that's going to hold for us, the information it's going to hold, is what is the tile, or what are the tiles it can walk through. In the case of ground-based unit, we're going to check if it's less than or equal to that. When we eventually get to naval units and air units, they'll have to check things a little bit differently, but that's future us's problem. For now, let's just do this for a ground unit. Now, the first thing we're going to do is we're going to give this a return path so it stops complaining. And this is going to be at the end. If we haven't found a path, we're going to tell ourselves in a debug that no path was found. And then we're going to return a new list of vector2s, and we're going to make this path vect. Actually, we're going to do list vector2. I'm declaring this wrong spot. Let's declare this at the top, because this is how we're going to return things. And then we can just add the start position to that, dot add. And we're going to add the starting position so that we return something, because our unit will be somewhere. And then we can just return that value, so path vect. So this way, we return something, this stops complaining, and if we get through all the code we're about to write, we get to the end, that means a path has not been found, so let's just return the starting node back to the unit, and that prevents anything from being complained about. Okay. So we need to actually get our nodes based on our coordinates. So let's go over to our path grid, and we're going to write a new function in here. we're going to write a new function as a path node that we're going to return. We're going to call this getNode. So this is how we're going to get the node data we need from the grid itself, since this is a private grid, because we don't want it being changed by the other scripts. In this case, we're going to take in the coordinates. Actually, let's take this as a vector 2, our position. So we're going to have to calculate out our integer values that go into the grid XY based on our coordinate position in the game view. So what we need to do is we need to go pos.y is equal to mathf.round to int pos.y divided by 0.86, because of course we multiplied by 0.86 when we create the nodes. And then we're going to check if pos.y remainder 2 is equal to 0. We're then going to need to subtract 0.5 from x, because we add 0.5 to x. Oh, that is not the right symbol. Remainder 2. Because we add 0.5 to x when we generate the grid on every other row, so now we need to subtract it. So this should return 2 integer values. And then we're going to return the grid value at that location. So return grid. So for the x, though, because it's not an integer, we're going to have to cast it to an integer, pos.x. And then we are going to want pos.y. Okay. So this is going to return a grid coordinate. Oh, we need to make that integer too, even though we did round it. This is going to return the grid with the XY values that correspond to this coordinate position. We're going to also need another path node return that can get the node as an integer from the integer values themselves. So get node int. We're going to take in an integer x and an integer y for that one. And that is going to be super simple. We're just going to return grid at x comma y and done. Okay, so these are how we're going to get the nodes from our pathfinding script. So the first thing we need is we need to get the node for our start position and for our end position. So we're going to call that path node start pos, and that is going to be equal to the grid dot get node get node. So this is going to take the actual coordinates of our start position. And then we're going to do the same. Oh, sorry, this shouldn't be start pod. This should be start node. And then we can copy that and make this our end node based on our end position. So this should return a node for our start position and end position. Let's make sure the positions we're trying to start from and go to actually exist in our grid. So we're going to check if it's null. The start node is null, or the end node is equal to null. We are going to basically want to return our path vect, our list of that, again, as basically nothing. In this case, invalid positions. Let's call it that. And then we return that, so we have a return path. If, though, we haven't returned anything, that means our start position and end positions do exist as nodes, and we should be able to start going through them. We have our open nodes list. We're going to make that equal to a new list path node, and then we're going to use our curly brackets. This is how CodeMonkey did it, and it's much smarter than the way I usually do it. So we're going to add that in that way so that we have a new list with the first item being the start node in the open nodes. Our closed nodes is going to be empty, so we want to make sure that's empty whenever we start our pathfinding, because we don't want anything left over from a previous pathfinding attempt. Regular brackets for that one. And we have to capitalize path node correctly. Okay, so now we want to go through and we want to clear all of our pathfinding data. So that is, if we remember the path node, we have the G cost, H cost, and F cost. They need to be set for every pathfinding operation. So we actually need to clear those so that we can properly set them. So we're going to go through all of our nodes, and actually let's go to the path grid, and we're going to grab this guy. So we have the width. This is going to be the grid.width because we haven't set it here. And we have the height, the grid.height. And let's correct the brackets. And so in this, we need to get the node at that coordinate. And this is why we have the get node integer, because we're going to do this using the XY here, it's just going to be faster that way. We don't have to try and convert the XY to coordinate positions and then send them back in and redo it. Now, we're going to then go to our path node. We're going to set the G cost of it to being an extremely high value. The reason we're doing that is because what we want to do is check if our G cost is lower than the new one we're going to be calculating as we go through the pathfinding. We then want to overwrite it, but otherwise we want to leave it. So we have to make sure this is higher than any possible pathfinding operation can get to. And you're never going to do a path that's this far. Okay, so we then need to do our calculate fcost function for the tile, for all the tiles, which is going to basically make our f equal to this huge number, because it's going to be g cost plus nothing, because the h cost is nothing. So the f cost is going to become that big number. And then we are going to want to make sure that we clear all of the came from node data for all the paths. So again, we erase that from any previous pathfinding. And let's fix this debug. Okay, so we've cleared our grid. We now need to get our starting point and establish that as our first node and calculate it properly. So our starting node is going to have a G cost of 0, because as we said, the G cost is the distance that the unit has had to travel to get here. Well, it hasn't had to travel to get to the start node. We then need to set the H cost. So the H cost is going to need to be calculated, so we need to get a function to do that. And the H cost is, as I mentioned earlier, the distance as the crow flies between our current tile and our desired destination. So we're going to want to write a new function. We'll just make this a private float for this, and we'll call this calculate distance. Let's do that properly. And we're going to be taking in a vector 2 of the A position, whatever our first node is, and a vector 2 of the B position. And then all we have to do is take the x distance is going to be equal to math f dot the absolute value of a dot x minus b dot x, because we don't care which direction we're traveling, we just care how far it is. And then we can calculate the y distance is equal to the same thing. If equal sign math f dot absolute. And that's going to be equal to a dot y minus b dot y. So the absolute value of that. And then we're just going to return a new float of the x distance plus the y distance. So that will give us our distance from one vector to the other. So when we want to use that, we can do the start node dot h cost is equal to calculate distance. So all we need to do is we need to take our start node dot position in one and our end node dot position in the other. And that will give us the distance between our nodes. And then we are going to calculate the f cost. We always calculate the f cost. Calculate f cost to get that set. And we have our starting node information. Okay, so now we need to actually start going through the tiles surrounding the starting node and performing these calculations on those tiles when it is appropriate. So we're going to use a while loop, and we're going to just take in we're going to do this so long as we have open nodes to investigate. So that's why we have that list of open nodes. And the first thing we are going to do is we're going to want to get in our list of nodes the node that has the lowest f cost. The reason for that is the node with the lowest f cost is the most likely to be the one between your current position and where you want to go. So we need to write a function for that. Let's do a new one. And again, this is going to return a path node. So we're going to make this a private function that returns a path node. And we're going to call that get lowest f. We don't need to take any conditions. So we're going to declare the lowest f path node as lowest f. And we're going to make that equal to the first of the open nodes. We're going to make that equal to 0. Open node 0. Okay, so we then will loop through our open nodes. And less than open nodes dot count. So loop through all of them. And what we're going to do is we're going to check, is the one we're currently looking at, if open nodes n, is the f cost lower than our current lowest f cost? So again, these are both path nodes, so we can just take the f cost as a variable since we've set that earlier. And if this is lower, we're then going to basically make our new node equal to our lowest f node. Pretty simple. And then we are going to, at the end of that, return that value or that node. And so we can look through all of our nodes that are open, and we can check which one is the best one for us to pull. And that's how the A star works. So you start with your starting node, you go to the neighboring ones, figure out which one has the lowest addition of the cost to walk there plus the distance as the crow flies to the end node. And that's the one you want to look at next, and you repeat that until you either get there or you find out, oh, we hit a dead end. Okay, let's go all the way back and find the next best one and start working through that one. And it's going to crawl its way to the end. So long as we have open nodes to look at, we're going to first go through all the open nodes, and we're going to grab a current node, being the lowest F, to evaluate. So this is the one we want, the node we want to look at. So what we need to do is check, is it the end? Have we actually found the path? And if we have, we're going to calculate the path and return it. We're going to leave this empty for now. We're going to write that function after. Now, because we are checking a node, we are going to remove it from the open nodes, and we are going to add it to the closed nodes. So we're just going to shift it over, add, and then current node. So this way, any node that we look at instantly gets moved to the closed node, so this will eventually run out. Oh, I am realizing that should be openNodes.count. I am so silly. So the while loop is going to go through the count of the open nodes. That's why that was rad. Okay, so now we need to basically, at this node, we need to go through all the neighbors. We need to add them to the open nodes and calculate their costs. So we need a function to actually get the neighbors in the first place. And this gets a little bit tricky because we also have to make sure that there's actually, that we're still on the grid. So we're going to return this as a list of path nodes. All right, path node, and then that is going to be called get neighbors, and we're going to spell it the proper Canadian way. Path node, current node is what we're going to take in. So in this, we're going to declare a new path node list. So new list path node, and then this is going to be called the neighbor list, and that's going to be equal to a new list, and then path node. Enter that. Okay, so we need to populate this list, but we also need to check to make sure we're within the grid. Oh yeah, and let's just return that right away. Okay, so the first thing we need to do is go the x minus 1 and the x plus 1. So we actually need to check though. So current node dot pause dot x minus 1 is greater than 0. We want to make sure that is before we go adding this. We're going to add then the neighbor list dot add, and then we're going to take the grid dot get node, and we're going to do our current node position, so the one we passed in, and dot pause minus new vector 2, and that's going to be 1, 0. Okay. So we should get a new node at, in this case, minus 1. Now we need to go the other way on the x-axis. So if current_node.pos.x plus 1 is less than the width, so grid.width, we then want to add 1 to this. Okay, so left and right, those are nice and easy. But now we have to do the diagonals. So we're going to do the diagonal left, diagonal up first. So in this case, we have to make sure the y value is actually within the grid. So we have to check if the mathf.round, I had to round this off because if I didn't round this, sometimes with rounding error meant it would look at these tiles anyway. So in this, we want the current node.y plus 0.86f, and then we want to take that and divide it by 0.86f, and that should give us the correct coordinate position of that. And we want to see if that is less than the grid.height. So the rounding was necessary for that. Oh, pause.y. And then if that's true, we can then basically do our x values as well, because we still need to check if the x values there are okay. So in this case, we're going to actually add a vector of -1, and we're going to add plus 0.86f. So that's going to be our new position vertically. So this is up and to the left, and then we check the x position +1 and make sure that it's on the grid, and we're going to add on 0.86f to that. So our up is done. We're going to copy that. We're going to bring it on down, and we're going to grab the neighbors that are down. So we have to go, this one's easier. We can get rid of our rounding thing. We can get rid of all of this because we're just going to make sure that if we subtract 0.86, it is less or greater than 0. And then the x is the same, and then all we have to do is make these minus. So this is going to return up to our 6 surrounding tiles, but it's not going to return any that are off the grid. At least hopefully not. This should work just fine. So we can get that list of tiles, and then we can go through them and do our proper evaluation. So we're going to use a for each loop for this. And we're going to take the path node neighbor. We're going to call it neighbor, lowercase. And we're going to do in get neighbors. So neighbors of our current node. So that will return up to 6 neighbors to evaluate, and we can go through them. So in this, we can then check, firstly, if we've already evaluated, if it's already in the closed nodes. If it hasn't been opened, if it's been closed, it's already been shut off. We don't need to look at it again. So we go close nodes dot contains our neighbor. So if that's true, we just want to continue. We don't want to end the loop because we want to go through all the rest of the neighbors, but we don't want to look at this one anymore because it's already been evaluated. The next thing we need to do is check, can we actually pass through this neighbor? So we're going to do if neighbor.open, and in the case of land units, if the unit type, if the open is greater than the unit type, that means it's impassable. So if we set our ground unit, our spearman, our scout, whatever, has a unit type of 2, meaning they can walk on ground of 0, 1, or 2, but they try to hit a mountain that's 10, well, we want to fail that as well. So the first thing we need to do when we fail it is we need to add the node to our closed nodes. We don't actually need to even do any calculations on it. We just need to get rid of it, and then we need to continue. Okay, so otherwise, though, if we can actually walk into it, we now need to do our calculations like we did with the start node. So we're going to calculate a new G cost. And in this case, it's going to be our current node's G cost. Node.gcost plus 1. Because with hexagon tiles, your distance center to center is always going to be 1. It's even. If you're doing a square grid and they can walk on a diagonal, sometimes you add 1, sometimes 1.44, depending on which direction they're moving in. But in this case, it's always going to be 1. Now, if our new gcost is less than our neighbor.gcost, we are then going to want to do the rest of the calculations. Because if we've evaluated, if this tile's in the open nodes, but something else has already found a quicker path to it, the gcost might be set to lower, and we don't want to redo that. We don't want to say, oh, follow this weird wonky path through instead. We only want to be adding in the gcost and calculating out our current, or adding in all the new information, so the came from node and the new f cost and all that, if this is a better route to this tile. Okay, so we're going to set, in this case, the neighbor.came from node as our current node, so we know how we got here. We then want to set its gcost. .gcost is equal to new gcost that we just calculated. We then want to calculate our hcost for this tile. So we're going to do that the exact same way as before. So neighbor.hcost is equal to calculate the distance, and we're going to be going from our neighbor.position to our end position or no, it should be end node.position. There we go. Although that should be the same thing. Okay, so we have that, and then after we have that calculated distance and set the h cost, we can do our calculate f cost. And finally, we can check, is this in the open nodes? And if not, we can add it to the open nodes, because we want to evaluate, until we get to the end, we want to basically go to this tile and be able to evaluate it as well. So our neighbor, oh my goodness, I cannot type at the moment. So if it's not in the open nodes list, add it to the open nodes list so we can actually progress. Okay, so we have that. So we can now calculate through all the tiles until we hit the end, but we're not yet returning a path. But if we look at this, for every tile we've gone through and found the most efficient path to it, so the G cost is the distance to get from the unit to that tile by walking, we know what node it came from. So all we have to do to return a path is we need to go through all of our closed nodes and then grab the came from node, and we can then work our way all the way to the front, because we're only setting the came from node when we can get to this node efficiently. So let's write a new function, and we're going to basically make this as a return a vector2 list of our path. Again, we want to do a vector2 instead of a path node, because we can then just feed this directly to the unit, and he will walk, or he or she will walk exactly where they need to in the coordinates, instead of having to grab the coordinates. So we're going to call this calculate path, and we're going to put in the end node that we had before, because that won't be in the closed nodes. And we need to go through the list. We need to generate a list of our path nodes, and we're just going to call this path. And this is going to be a new list of path nodes. We have written that line of code many a time. So we have our new list for our path, and we're not going to return that because, again, it is a list of path nodes, and we want to return a list of vectors. So what we need to do, though, we're going to path.add the end node. Oh, I'm returning my efficient way. I could have added the end node immediately, but whatever, this works fine. So path node, current node is going to be equal to the end node. This is where we're going to start evaluating it. Again, we want to, in the path, we need the end node because that's where we're ending up. Now, we're going to do a while loop, and we're going to say, well, the current node dot came from node is not equal to null. What this means is we haven't gone back to the starting location, because the only node in our path nodes list that won't have a came from node value set is our starting node. So we know that if the came from node exists, we're not back at the start. But once we don't have a came from node, we are at our starting position, and we can stop this loop. So we're going to do path.add, and we're going to add the current node dot came from node. So that's where it came from, and then we're going to set the current node to the current node dot came from node, so wherever it came from. So we're going to just basically, we're going to start at the end. We're going to go to the node it came from. We're going to add that to the path. We're then going to go to that node. We're going to add it to the path. We're going to go to that node, and we're going to continue until we get to our starting position. So that's very simple. Now we need to reverse that, because otherwise we're going to be trying to walk from the end to the start, whereas we want to go from the start to the end. And now let's take those nodes and put their positions into a new list of vector2. And this is going to be the path vector that we're going to return. And we're just going to make this a new list for now. New list vector2. And we're going to go through our path that we calculated before, and less than path.count, and then n++. And for each of those, we're going to add to the path vector dot add our path dot position. Path n dot position. There we go. So our vector2 position stored in the path node object or class is then going to be passed into the path vector, and then we can return path vector. So our calculate path now actually results in a route. So we go here when the current node is equal to the end node. When we've calculated our way to it, we are then going to very simply return that so our unit can get it. So return calc path, and then we're going to feed in our current node, which is also the end node. You can write either, that is fine. So we have a way to pathfind. So this will calculate out a path from our starting position to our ending position based on the unit type's ability to walk. Okay, but we have no way of using this yet. So we're going to need a unit and a couple of scripts just to quickly control that unit and to tell it when to pathfind. So in our art, I have this little scout. I don't even know where he is. Let's set his position though. So he's going to end up sort of in the middle of the map. So 35 and like 8 because our map is going to be 20 by 50. Oh, 25 and 8 because it's going to be 20 by 50. We set that before. Now we want to add in a box or a polygon collider for him, but we already have one that's the exact shape we want. So let's go to our hexagon in our resources folder. Let's grab its polygon collider. So copy that. Let's go back to our scene and let us paste that on this guy. I think I have to add the polygon collider, and then let's paste our component values so that he gets the proper shape collider. This way we can click on him. Now we don't want him on the default layer, so I've made a new layer called units. Let's put him in that. That way we don't accidentally click on him or he doesn't mess with the pathfinding script. And now we're going to need a script, firstly to control him, and then a script to actually tell him when to pathfind. So unit control. And this is in this script, we're going to use this to actually walk him around the map. So come on, open up. So this is a mono behavior that's going to stay as that. We're going to want to be able to take in a path. So we're going to have a public list vector2 that's going to be our path. And we're actually going to set it as a blank list right now because we need to be able to check if it's actually full of anything. So list vector2, we'll set that blank. We're also going to want an integer to determine where in the path we are. So we're going to call that cur node. We're going to set that to 0. And then I'm not going to animate him walking. I'm just going to teleport him tile to tile along the path. And so we want a float that we can use to track how quickly he's moving tile to tile. So that way he doesn't just instantly teleport to the end of the path and we can actually watch him. Okay, so we don't need anything in the start function. What we do need is in the update function, we're going to basically check if we have a path. We are going to start pathfinding. Or we're going to start walking the path. Sorry, we have path found at this point. So if delay is greater than or equal to 0.5f, so every half second we're going to move one tile. The first thing we're going to do is we're going to check, is there actually a tile there? Just in case something is going wrong. Also, in the case of, because we're not compensating for the map movement and the tiles getting moved around, in this case, this will turn it off when he reaches the edge of the map because it's moved. And we're going to fix that in a future episode. But this episode's already getting extremely long, so we don't want to do that yet. So anyway, we're going to check, though, path current node. So, and then path cur node. This is just my habit. And then no length to that. And we're going to check the default mask. Mask.get mask. And we don't have to do this very often, so I'm just going to set it here. So we check, have we actually hit a tile? And if so, we're going to want to move to it. So let's actually write that right now. So the move to is going to be a fairly simple function. So we're going to do void move to, and then we're going to put in a game object. And we're going to call that hex. So that's the tile we want to move to. And what we're going to do simply is we're going to make our position, transform.position, is going to be equal to hex.transform.position. And then we're going to set our parent object to that tile because we want to make sure that whenever we move the camera, our units move, like stay on the tile they're on. So when the tiles get moved by our camera controller script down here, where we actually move the tiles, the units will get moved with them because they're going to be a child of that tile. So we set parent equal to hex.transform. This unit will now move with that tile. So we're going to make the delay equal to 0. And then we're going to do our current node plus equal to 1. And if we're at the end, so if cur node is greater than equal to path node dot, dot count. So we know we're out of nodes. We want to basically reset the path to a blank list. Goes new list. Oh, this is a vector2 list. And we then want current node to equal to 0, and we want delay to equal to 0.5f. So we're basically resetting everything. Oh, it's not path node, it's path.count. There we go. So if our current node is greater than or equal to our count of nodes we're supposed to go to, we just reset everything. So now we can go back here, and we can say move to hit.collider.gameObject. And that way, again, we send through the game object because then we can move to it and make it the parent of the unit. If, though, we don't find a tile, we want to tell ourselves that. Now we should, but we should find a tile, but again, we might not. So we want to say no tile found. And then we want to, again, we can just copy from down here. We want to erase the path so the unit stops trying to walk. And now, otherwise, though, we need to then tick our delay up so we actually walk. So we're going to add time.delta time to our delay. So this way, we will walk one tile every half second along the path. Fix that error. And then until we reach the end of the path. So we have our unit control script. Great. Now we need to actually find a way to tell the unit to do that. So first of all, let's go to our little guy here. Let's add on our unit control script. And now we need to talk to this. One thing I do need to double check is, did I make that? Yep, it's all public. So we are good. We are going to be able to set this from another script. So we're going to call that script just controls. So our control script is going to start out fairly simple, and then as time goes on, it can get more and more complex. But we want to track, firstly, we want to track, do we have a unit selected? Object unit. And that's all we need there. We're going to check if we've pressed the mouse. Input dot mouse button down. Or mouse button up, sorry. I prefer to do this on the up, so somebody can start clicking down, realize they want to move their mouse to something else, so they miss the thing, and then release it. So this will make sure of that. We then want to get our camera or our mouse position in relation to the camera's view. So we've done this before, but we're going to just type it out again. So camera.main.screen to world point. There it is. And then inputs.mouse position. So that's going to give us whatever our mouse is hovering over. So we have our coordinates of our mouse. So then we want to check, do we actually have a unit selected or not? So if we don't have a unit selected, we need to try to select a unit. So if unit is equal to null, we're going to do a raycast. Cast hit 2D. And hits is equal to physics 2D. Dot raycast. And then we're going to check our position that we have. Position, no distance. And then we're going to want that units mask. We put the unit on, get mask. Units. Okay. And then if we hit something, again, we're going to hit a unit. Now at this point, all the units, if hit, all the units are just going to be one type. So we don't need to check anything else. In the future, we can check if the units are enemy units or whatever. But for now, we're just going to set unit equal to hit.collider.gameObject. Because again, if it's on the units layer, it's going to be a unit. Okay, so if we don't have a unit selected though, we need to, or if we do have a unit selected, we need to either deselect it, select a new unit, or try to pathfind. So the first thing we can do is we can copy this. Now, in this case, though, if we hit, we're going to do something a little bit different. So if we hit a unit while we have a unit selected, we want to check, is it the unit we have selected? If hit.collider.gameObject is equal to the currently selected unit, we want to make unit equal to null. We want to deselect it. Otherwise, though, we want to select our new unit. And let's copy that again. There we go. So this way, we can, if we have multiple units on the field, we can select different ones. Okay. Now, if we didn't hit a unit, we want to check if we can pathfind, because we don't want to pathfind into a unit that's already standing there. So in this case, we're going to do a raycast. And we're going to do the default layer instead. So default. Okay, and then again, default is only tiles in our code. So if we hit it, we need to, oh, it's complaining, so we don't actually need that. Oh yeah, because we already did it here. So we're going to redeclare the hit as a default hit. And then we are going to go to the unit. We're going to get the unit's control component, control, and we're going to set the path. We're basically going to do the reset. So we're going to do the path equals new list. This way, if it's pathfinding somewhere currently, this will basically reset everything. New list vector 2, unit.get components, unit control. I should just be copying and pasting. Dot current node. We want that to be equal to 0. And then, yeah, let's just copy this. And then we want to set the delay equal to 0.5 f. And then the last thing we want to do is set the path to. So we're going to get the pathfinding component, which is also, we're going to attach this to the camera so we can just get it. So pathfinding. Actually, I hit a wrong key there. And then we're going to do dot get path. And what we want is we want the unit.transform.position. So that's going to be a grid position, and then we're going to want the hit.collider.gameObject.transform. Oh my goodness, transform.position. Okay, so, then we of course need to send through our unit type. So in this case, the land unit, we're going to set through 3, so that it won't be able to walk on water or through mountains. But yeah, this will take in the unit's current position, and it's going to send it to the whatever tile we clicked on, and hopefully calculate a path. So hopefully that's everything we need. Let's go back into our game, and in our camera, we're going to need to attach that unit control, and we're also going to need to attach our pathfinding script. We hadn't even done that yet. So we have those attached, and then the grid, we can just drag the camera over here, and that's going to set the grid, because again, it's on the same object. So we can save that. Now let's just double check our unit has the unit control script, and it's set to the unit's layer. Okay, let's test this out. We've done a lot of coding. We've been staring at the coding screen. Now let's test it. So we, of course, we want to start a guy on land. So let's just use the scene view to move him onto land. In a real game, you could just spawn him on land, but let's get him nicely on top of a tile. That looks like he's pretty close to right on top. So let's go to the game, let's click him. We have nothing to indicate that he has been selected, but we didn't get an error, so that's good. And let's click somewhere, and nothing happened. So, why did nothing happen? Oh, I know why. We attached the unit control script instead of the control script. That's my bad. Control script. Okay, let's go back in. And alright, so once again, he's standing in an ocean. So back to scene view. Let's move him over. Not the camera, the unit, please. Oop, there he is. Let's drag him over to land. Let's get him positioned. So right about there, close enough. Go into our game, so we'll click him, and let's just click somewhere. And then, okay, that's a pretty simple path find. Alright, so he's still selected. Let's click over here and see what he does. Oh, I'm noticing a quick little error. One thing we want to do with our scout unit there is we want to, oh, he is a child of an object. So we want to set his order and layer to something a little higher. So that way he's going to appear above the hills. But so far it seems like it's working. We're getting there. All right, let's put him on this tile. Okay, let's select him, and then let's just try to walk around this little water. And look at that, he walks around. A little funky bit there. Oh, that's deselecting him. Select him again. And he teleported. Okay, so you'll probably see a little bit of an edit there. To jump to this screen, I just realized a little thing in the code I forgot to change. When we are doing our position calculations here, under the y-axis, these should be 0.5f. That's why he's running around a little bit wonky. So 0.5f, and then 0.5 on these guys. And 0.5f. Okay, There we go. So I just took a minute to figure that out. That should fix things. Alright, again, scene view. He's always ending up in the water. Drag him over here. Close enough. Click, and let's pathfind this way. And he's walking around the water nicely. And okay, let's pathfind back. And again, he's walking around the water tiles. And he gets to where he wants to. If we click on a water tile, we get no path found because he can't go to water. If we try to go all the way over here, he's going to be able to walk over there, I think. That looks pretty good. And again, if we go up, he should go around those water tiles, and there we go. He is pathfinding. And he errors out. He can't pathfind everywhere. He can't cross the water. He can't cross the mountains. So, there we have it. A very simple A-star pathfinding script. Again, I have to thank CodeMonkey and his tutorial on how to do A-star pathfinding in Unity. And of course, in this version, we've adapted it to work on this hexagon-based grid. Now, one thing though, is if we move the map and the tiles move, if we go back to scene view, the map is no longer under the grid. So if we try to pathfind again, we're just going to get an error because we're clicking out of the range of the grid. So in the next episode, we'll cover how to compensate for the map movement and the offset we need to calculate so that we can basically take all the numbers from over here that we want and translate them back to where the grid is and then back to where the unit is for when we want them to start moving. Anyway, if you made it this far, thank you for watching, and as always, have a good one.